Alright, so the lecture I chose to talk about is the one by Richard Steiner, How the Planck's Constant is Better than the Kilogram. So currently the kilogram is the only SI unit of measurement that is not tied to a fundamental constant. The way the kilogram is defined is it's just the mass that 1 liter of water takes up at 4 degrees Celsius. So this may seem like a pretty accurate representation of what a kilogram is, but really there's a lot of margin for error. The water could not be the correct temperature, so it would have a different mass. There could be impurities in the water, or you could really just not measure a liter because it has to be exact. So what Richard Steiner and the people at NIST, National Institute of Standards and Technology, are saying is we should use the Planck's constant to define the kilogram. Planck's constant is a fundamental constant that is the ratio between energy and frequency of a photon, so it would lead to a much more exact way to measure the mass of a proton, or of a kilogram, excuse me. So the largest uncertainty for a kilogram right now, the different, kind of the standard deviation of how much it weighs, is about 20 micrograms, which is incredibly small, but when we're using this for applications in the science and technology field, it can be pretty significant. If we use Planck's constant, the estimations are that it'd be about 100 times less uncertain. So that's definitely good in fields of science and technology. Really no plans have been made yet about when the change will take place and when we will start to define define the kilogram through Planck's constant, but it's scheduled to happen around the middle of 2014. So currently there are just these weights, these kilograms, that are kept in kind of vaults around the world, like places similar to NIST in other countries and at NIST. And the problem is they're decaying. They're just interacting with the atmosphere and their mass is changing. So that's why we need something that is tied to a fundamental constant, not just this sort of arbitrary mass that's kept somewhere in these vaults. So a lot of people may think, this is pretty insignificant because 20 micrograms is about one 1/1 billionth of a kilogram. So it's pretty insignificant, but when you're using it for applications in science and technology, these really small amounts can matter a lot. So the more and more precise we can get them, the more and more precise we can make our instruments. So yeah, I think that's a pretty cool way that how all SI units are defined by fundamental constants, and things like the Planck's constant, the kilogram, that may not seem really related, are actually related and very significant to each other.